Imagine this. You're an astronaut, floating peacefully in space, when suddenly you're pulled toward a monstrous black hole. As you cross that invisible line, the event horizon, everything changes. Space isn't space anymore. It becomes time. You can't turn back, can't even stand still. You're hurtling toward a point where physics as we know it just breaks. Sound terrifying? Or maybe exhilarating? That's exactly what we're unpacking today in this video. Inside a black hole where space becomes time. If you've ever wondered what happens to the tiniest building blocks of matter, like quarks, when they get sucked into these cosmic vacuum cleaners, stick around. We're going to break it down step by step with mind-bending science, some fun analogies, and no PhD required. Hit that like button if you're ready to have your brain twisted, and let's jump in. First off, let's set the stage. Black holes aren't just sci-fi villains. They're real. And they're out there right now, lurking in the hearts of galaxies. Picture a star that's run out of fuel, maybe 10 times the mass of our sun. It collapses under its own gravity, crunching down into a point so dense that not even light can escape. That's the singularity at the core. Around it, the event horizon, that infamous point of no return. Once you cross it, gravity's grip is absolute. But here's the kicker. From the outside, black holes look pretty straightforward. Dark, mysterious orbs. Inside? What if the insane forces inside a black hole could rip apart quarks, the fundamental particles inside protons and neutrons, over and over, creating an infinite explosion that remakes the universe? Spoiler, it doesn't happen. But the why is fascinating. Let's build this up from the basics so you can follow along. Okay, rewind to Black Holes 101. Gravity isn't uniform everywhere. It's stronger closer to the source. That's why, as you approach a black hole, your feet feel a stronger pull than your head. This difference is called tidal force, and it leads to something gruesomely nicknamed Spaghettification. Yeah, you heard that right. Your body gets stretched like pasta. For a small black hole, say one with the mass of a few suns, this happens way before the event horizon. But for supermassive ones, like the beast at the center of our Milky Way, Sagittarius A star, about 4 million solar masses, you might cross the horizon without feeling a thing. At first, the tidal forces ramp up as you plunge deeper. Now, scale that down to the atomic level. Atoms get torn apart, then nuclei, then protons and neutrons. But what about quarks? Those are the even tinier bits that make up protons. 2 up quarks and 1 down, and neutrons, 1 up and 2 down. Quarks aren't loners. They're glued together by the strong nuclear force, carried by particles called gluons. It's one of the 4 fundamental forces, way stronger than gravity or electromagnetism up close. Here's where quantum chromodynamics, or QCD, comes in. QCD is the theory that explains how quarks and gluons interact. The strong force doesn't weaken with distance like gravity does. It actually gets stronger the farther you try to pull quarks apart. It's like a cosmic rubber band that snaps back with vengeance. In fact, you can't isolate a single quark. If you pump in enough energy to separate them, say in a particle accelerator like the Large Hadron Collider, boom! That energy creates new quark-antiquark pairs instead. It's called confinement. Instead of free quarks, you get a spray of new particles like mesons or baryons. This process is called hadronization, and it's why we never see naked quarks wandering around. Now, back to the black hole. Imagine quarks being stretched apart endlessly, each separation birthing more quarks from the energy, leading to an infinite cascade, a quark catastrophe that might explode the black hole or even rewrite reality. It's a wild idea, right? Like a chain reaction gone cosmic. But as Brian Cox explains, it doesn't work that way. First, energy conservation is king. Pulling quarks apart isn't free. It requires massive energy input. In a black hole, that energy comes from the gravitational field. But it's not infinite. The system has limits. More importantly, time is the ultimate buzzkill here. Let's talk about time inside a black hole. This is the part that flips your perception of reality. According to Einstein's general relativity, gravity warps spacetime. Near a black hole, time slows down for outsiders watching you fall in. That's time dilation. But from your perspective, things seem normal until you cross the event horizon. Inside, space and time swap roles. What we think of as radial direction, toward the center, becomes time-like. You can't avoid moving forward in space any more than you can avoid moving forward in time right now. It's like being on a one-way conveyor belt to the singularity. No loitering, no infinite loops. For a supermassive black hole, the time it takes you, from your viewpoint, to reach the singularity is finite. Maybe hours or a day, depending on the size. For a black hole with one solar mass, it's microseconds. Scale up to billions of solar masses like M87's monster, and it's around a day. The point is, it's not eternal. Whatever quark ripping happens, it stops when you hit the singularity, where density goes infinite and our laws of physics throw in the towel. But why does this matter? Because an infinite catastrophe would need infinite time or space to play out. Here, time runs out. Cox points out that singularities are probably not the end game. They're a sign that general relativity needs a quantum upgrade. Enter quantum gravity theories like string theory or loop quantum gravity. In string theory, everything's made of vibrating strings, and singularities might resolve into fuzzy, non-infinite points. Loop quantum gravity suggests space-time is quantized, like pixels, preventing true infinities. We don't know yet. It's cutting-edge stuff, with experiments like LIGO detecting gravitational waves giving us clues. Hawking radiation adds another layer. Black holes aren't eternal. They evaporate over insane timescales, leaking information back out. But that's a whole other video. Comment below if you want me to cover that. Did you know the first black hole image from 2019 was of M87's? It looked like a blurry donut, but it proved Einstein right again. Or that if our sun became a black hole, it won't, too small, its event horizon would be just 3 kilometers across? Earth wouldn't even notice, gravitationally speaking. Back to quarks. There are 6 types: up, down, charm, strange, top, bottom. But only up and down make everyday matter. The strong force is color-charged, like RGB for quarks, which is why they're confined in color-neutral groups. Analogy time. Think of quarks as party animals who hate being alone. They always drag friends along if you try to split them up. So, wrapping this up, inside a black hole, space becomes time. Tidal forces shred everything. But quarks don't trigger an endless apocalypse. The finite journey to the singularity puts the kibosh on that. It's a reminder of how much we still don't know about the universe's extremes. Black holes are like nature's ultimate stress test for physics, forcing us to merge quantum mechanics with gravity. If this blew your mind like it did mine, smash that subscribe button and turn on notifications. We've got more cosmic adventures coming, like wormholes or multiverses. What do you think happens at the singularity? Drop your theories in the comments, and I'll shout out the wildest ones in the next video. Thanks for watching, stay curious, and I'll see you in the next one.